Dear students, welcome to Commissionerate of Collegiate Education Learning Management System. In this presentation, I am going to discuss about two named reactions of carbonyl compounds. They are Aldol and Cannizzaro reactions. Myself, Vinny Teja, lecturer in chemistry, SKR and SKR Government Degree College for Women, Kadapa. At the end of this presentation, you will be able to write Aldol and Cannizzaro reactions. You can write the mechanism of Aldol condensation reaction in presence of base. You can describe crossed Aldol condensation reactions. You can even describe the intramolecular Aldol condensation reaction. And finally, you can also describe the mechanism of Cannizzaro reactions. So, in this video, I am going to discuss about Aldol reaction, its characteristics, the mechanism of Aldol reaction, and different types of Aldol reaction that are involved, namely crossed Aldol condensation reaction and intramolecular Aldol reaction at first. And later, I want to focus on next named reaction of today's topic, that is Cannizzaro reaction and its mechanism. An aldehyde or a ketone having alpha hydrogens undergoes self-condensation in the presence of dilute base to obtain beta-hydroxyaldehyde or beta-hydroxyketone, which upon dehydration generates alpha-beta unsaturated aldehyde or ketone. This reaction is called Aldol condensation reaction. An aromatic or aliphatic aldehyde having no alpha hydrogens undergoes disproportionation reaction in the presence of concentrated base to obtain salt of carboxylic acid and a primary alcohol. This reaction is called Cannizzaro reaction. Here we can find the difference by noticing the underlined part that Aldol reaction involves the carbonyl compounds with alpha hydrogens in dilute base, whereas Cannizzaro reaction involves the carbonyl compounds which have no alpha hydrogens in the presence of concentrated base. So let us understand both the reactions in detail. Let us discuss the first named reaction of today's topic, that is Aldol reaction. Aldehydes and ketones that have at least one alpha hydrogen atom undergo Aldol reaction. The carbon atom adjacent to carbonyl carbon is considered as alpha carbon, and the hydrogens present on alpha carbon atom are considered as alpha hydrogens. If you observe these two examples, acetaldehyde is having 3 alpha hydrogens, whereas acetone is having 6 alpha hydrogens. It is an addition reaction between two aldehydes or two ketones, or an aldehyde and a ketone in presence of aqueous base to give beta-hydroxyaldehyde or beta-hydroxyketone. When aldehydes participate in Aldol reaction, beta-hydroxyaldehyde is formed as a product, and these beta-hydroxyaldehydes are commonly known as aldol. When ketones participate in Aldol reaction, beta-hydroxyketone is formed as the product. The beta-hydroxyaldehyde or beta-hydroxyketone easily loses water when heated in presence of weak base to form alpha-beta unsaturated aldehyde or ketone. This process is called dehydration of aldol product. Aldol reaction and dehydration steps are catalyzed by both acid and base. Because the base catalyzed aldol reactions are familiar and important, let us restrict our discussion to base catalyzed aldol reactions. Coming to characteristics of aldol reaction, aldol reaction is a nucleophilic addition in which a carbon ion is the nucleophile. Among the two molecules of aldehyde or ketone, one molecule becomes a carbon ion, and another molecule serves as the electrophile because its carbonyl carbon is electron deficient. Presence of alpha hydrogen in aldehyde or ketone is the essential condition for Aldol reaction because only such type of carbonyl compounds forms carbanion in the presence of base. Let us revise what is a nucleophile. It is a chemical species that donates an electron pair to form a bond in a reaction. Nucleophiles are either negatively charged or molecules with lone pair of electrons. An electrophile is an electron pair acceptor. Electrophiles are positively charged or neutral species having vacant orbitals which are attracted to an electron-rich center. This is how nucleophile attacks an electrophile. Some examples of aldehydes and ketones that undergo Aldol reaction are given below. In all the examples, alpha hydrogens are marked in red color. Aldehydes and ketones that have no alpha hydrogen atom do not undergo Aldol reaction. For example, formaldehyde, benzaldehyde, diphenyl methanone, all these examples do not have alpha hydrogen in it. Since there is no availability of alpha hydrogen atoms in the above compounds, these do not participate in Aldol reaction. However, in the presence of concentrated base, they undergo Cannizzaro reaction. Now, let us focus on the mechanism of Aldol reaction. Treatment of acetaldehyde with an aqueous base produces 3-hydroxybutanol. Acetaldehyde molecule in the presence of aqueous NaOH gives 3-hydroxybutanol. This mechanism occurs in 3 steps. In the first step, carbanion is generated, and in the second step, nucleophilic attack of carbanion takes place, and in the third step, protonation results in the formation of beta-hydroxyaldehyde. Attack of base to remove a proton from alpha carbon of aldehyde generates resonance stabilized carbanion. This is how the carbanion that is formed in the step 1 gets resonance stabilized with its enolate ion. The carbanion that is formed in step 1 acts as a nucleophile and it attacks the electrophilic carbonyl carbon of second molecule of aldehyde, thus forming a new carbon-carbon bond, and this product here it is called alkoxide ion. The alkoxide ion that is formed in the step 2 receives a proton from solution and gets protonized to give beta-hydroxyaldehyde. The beta-hydroxycarbonyl compound formed in the Aldol reaction dehydrate more readily in the presence of base. This dehydration mechanism with base completes in 2 steps. In the first step, base removes a proton from alpha carbon forming a resonance stabilized enolate ion. In the second step, the electron pair of enolate forms the pi bond as OH- gets eliminated, thus forming alpha comma beta unsaturated carbonyl compound. Here it is alpha comma beta unsaturated aldehyde. Till now we have seen the mechanism of Aldol reaction in case of aldehydes. In case of ketones, the reaction mechanisms follows the same. Example, formation of beta-hydroxyketone from acetone. Formation of carbanion in the first step by the attack of base. Nucleophilic attack of carbanion on second ketone to form addition product. Protonation of the alkoxide ion obtained in step 2 generates beta-hydroxyketone. Dehydration of beta-hydroxyketone yields alpha comma beta unsaturated ketone. This is how the reaction mechanism of ketones occurs. If the mechanism involves steps 1 to 3 only, then it is termed as Aldol addition reaction or simply an Aldol reaction. But if dehydration step also takes place, then it becomes an Aldol condensation reaction because a water molecule is lost in this event. If the Aldol reaction occurs between same type of carbonyl compounds, as we have seen till now, that is reaction between acetaldehyde or reaction between acetone to give corresponding beta hydroxy carbonyl compound. Such reactions are called self-aldol condensation reactions or simply an-aldol reactions. But if aldol reaction occurs between two different carbonyl compounds, then it is called crossed aldol or mixed aldol reaction. For example, reaction between acetaldehyde and propanaldehyde. When two different aldehydes having alpha hydrogen atoms are combined in aldol reaction, four different products are formed because both the aldehydes can lose acidic alpha hydrogen atom and forms carbanion. Both the carbanions from different aldehydes can react with both the carbonyl compounds. If acetaldehyde molecule loses its one alpha hydrogen atom, then it becomes alpha carbanion. The formed carbanion of acetaldehyde reacts with this aldehyde for one time to give this product, and the alpha carbanion of acetaldehyde reacts with propanaldehyde to give this product. Similarly, if propanaldehyde loses alpha hydrogen and becomes carbanion, it reacts with itself to give this product, and it reacts with acetaldehyde for the second time to give this product. If two carbonyl compounds participate, then four different beta hydroxy carbonyl compounds are formed as the product. A cross-Dalton reaction occurs readily when one carbonyl component has specifically acidic alpha hydrogens. For example, cross-Dalton reaction between an aldehyde or ketone and a beta dicarbonyl compound. This is the beta dicarbonyl compound. Beta dicarbonyl compounds are called active methylene compounds because they are more reactive towards base than other carbonyl compounds. The alpha hydrogens between two carbonyl groups of beta dicarbonyl compounds are highly acidic and hence they can be easily removed by base. Therefore, beta dicarbonyl compound always becomes the carbanion in this aldol reaction. The remaining steps of this crossed aldol reaction are same as seen earlier. That is, attack of nucleophilic carbanion to form a new carbon-carbon bond in an intermediate, and then protonation followed by dehydration to give alpha comma beta unsaturated carbonyl compound. Intramolecular aldol reaction occurs in a molecule which has two carbonyl functional groups in the same molecule. Dicarbonyl compounds undergo aldol reaction to make 5 and 6 membered rings. In this reaction, the carbanion formed from one carbonyl group becomes nucleophile and the carbonyl carbon of another carbonyl group becomes electrophile. For example, treatment of 2,5 hexadione with base forms 5-membered ring. The intramolecular aldol reaction also follows the same mechanism, that is, formation of carbanion, nucleophilic attack of carbanion, and then protonation followed by dehydration. In the first step, base removes one of the alpha hydrogen to generate alpha carbanion, and this molecule can be redrawn for our convenience. And in the second step, the formed carbanion attacks the carbonyl carbon of second carbonyl functional group in the same molecule and generates 5-membered ring intermediate. In the third step, protonation of this intermediate followed by dehydration gives alpha comma beta unsaturated 5-membered carbonyl compound. In case of intramolecular aldol reaction, more stable 5-membered or 6-membered rings are formed. This is all about aldol condensation reaction. Now let us discuss the second named reaction of today's topic, that is Cannizzaro reaction. Cannizzaro reaction is named after its discoverer Stanislaw Cannizzaro. Aromatic and aliphatic aldehydes with no alpha hydrogen atom gives the Cannizzaro reaction when treated with concentrated sodium hydroxide or other strong bases. Among the two molecules of aldehyde that participate in Cannizzaro reaction, one molecule gets oxidized to form salt of carboxylic acid and another molecule of aldehyde gets reduced to primary alcohol. This simultaneous oxidation and reduction of aldehyde is called Cannizzaro reaction. Cannizzaro reaction is a disproportionation reaction, which means simultaneous oxidation and reduction occurs in the same compound. The aldehydes that undergo Cannizzaro reaction are given below. For example, formaldehyde, benzaldehyde, and aliphatic or aromatic aldehydes that have no alpha hydrogen in it. Cannizzaro reaction usually takes place with sodium or potassium hydroxide. For example, two molecules of aldehyde when treated in the presence of potassium hydroxide gives a primary alcohol and potassium salt of carboxylic acid. Here, salt of carboxylic acid is an oxidized product, whereas primary alcohol is the reduced product. When two molecules of benzaldehyde reacts with potassium hydroxide gives benzyl alcohol and potassium benzoate. Here, benzyl alcohol is the reduced product, whereas potassium benzoate is the oxidized product. Similarly, when benzaldehyde reacts with sodium hydroxide, it gives benzyl alcohol and sodium benzoate. Now, let us see how the Cannizzaro reaction mechanism is followed. The reaction is initiated by the nucleophilic addition of hydroxide ion onto the carbonyl group of an aldehyde molecule to give the corresponding anion. In a strongly basic medium, the anion formed in the step 1 gets deprotonated to give dianionic species, and this is the dianionic species. The dianionic species is highly unstable. It attains stability by transferring hydride ion to other aldehyde and gets oxidized to corresponding salt of carboxylic acid, whereas the second molecule of aldehyde is thereby reduced to alcohol. Therefore, the key step of Cannizzaro reaction is hydride transfer. Hydride ion transfer from dianionic species to the second carbonyl compound gives one oxidized product, that is potassium salt of carboxylic acid, and the second product receives a proton from the solution and gets reduced to primary alcohol. Therefore, hydride ion transfer from dianionic species results in the formation of salt of carboxylic acid as oxidized product and primary alcohol as reduced product. This is how the mechanism of Cannizzaro reaction occurs in aliphatic or aromatic aldehydes that have no alpha hydrogen in it. Let us summarize the points that we have discussed so far. We understood that aldol reaction is an addition reaction between two carbonyl compounds that have at least one alpha hydrogen to form beta hydroxy carbonyl compound. Reaction between two different carbonyl compounds is considered as crossed aldol condensation reaction. We have also discussed about intramolecular aldol reaction that In this case, 5-membered or 6-membered rings are formed. We have also discussed about Cannizzaro reaction that aromatic or aliphatic aldehydes that have no alpha hydrogen react with concentrated sodium hydroxide or other strong alkalis. This Cannizzaro reaction is a disproportionation reaction. That means simultaneous oxidation and reduction of a compound occurs. This simultaneous oxidation and reduction of an aldehyde that have no alpha hydrogens is considered as Cannizzaro reaction. I hope you have understood this presentation. Thank you.